Hello, everyone. Welcome to today's webinar, which is the ninth of a series organized for the 20th anniversary of Climate of the Past. So the two conveners today are Lyndon Ashcroft and I. This topic is past volcanic eruption, past volcanism climate. The webinar will last for 1 hour and 20 minutes. So we will have first two presentations of 25 minutes, and then we will have half an hour of Q&A. So you can put the question in the Q&A box whenever you want, but we will answer all the questions after the two seminars. All the webinar are recorded, and they are on the EGU YouTube channel. So thanks to the EGU office. So if you want to see this seminar again, or if you want to see some of the previous seminar, you can go on this YouTube channel. So volcanism is a very important element in the climate system because volcanic eruption induce among the strongest forcing on the general time scale. They induce a very abrupt cooling because of the injections of, in particular, of sulfates in the atmosphere. So it has a short-term cooling effect, but if you have a cluster of different eruptions, you could have a longer effect. And for instance, the volcanic activity is supposed to be one of the main forcing during the last millennium and explain at least partly the cooling between the 13th and 18th century, which is sometimes referred to as the Little Ice Age. It could also have some feedbacks with different elements. So we will hear more about that today. We have selected two speakers, Michael Siegel from the University of Oslo and Lauren Marshall for the University of St. Andrews. And Lyndon will say a few words before she introduces Michael. Thank you.
Thank you, Hugo. Hello, everybody. My name is Lyndon. I'm coming to you from Australia. I'd like to begin by acknowledging the lands of the Wurundjeri people of the Kulin Nation, where I'm talking to you from today, and pay my respects to elders past, present, and emerging, and extend that acknowledgement and respect to all traditional owners and First Nations people from around the world who have managed volcanic eruptions for a long, long time. I'd like to introduce our first speaker, Michael Siegel from the University of Oslo. Now, Michael's research is exploring environmental properties to identify and quantify the impact of perturbations in the climate system. This provides really important constraints to understand future climate prediction. We know here at Climate of the Past that the best way to understand the future is to go back in the past. His work does that. Michael's developed analytical and empirical approaches that have been setting new benchmarks in terms of precision and accuracy and scope within the field of ice core killer. Michael's recent scientific achievements have exceptionally large transformative implications for various research fields raised solar and space science, geology, human history, archaeology, and natural hazard assessment. Michael's going to give us a very interesting a story of fire and ice. Please, Michael, share your screen and take it away.
Okay, what I would like to present is an overview of how we can use the past to infer information about past volcanic eruptions and how these eruptions might have impacted weather and climate that also past human societies had to cope with. And the title of my presentation is coming from a novel, The Song of Ice and Fire, which became more famous through the TV adaptation Game of Thrones. And one of the leading motives of this story is winter is coming for the House of Stark. And this is reflecting very strong parallels to myths in the Norse culture, in Scandinavian culture, but also in German culture, of the Fenrir wolf swallowing the sun and 3 years of consecutive winter, which is the harbinger of large hardship for human society. And I will later argue that basically these myths might be founded in a real observed event of volcanic eruptions in the past. But before doing so, I would first jump into the period that Hugo already introduced, to the late Little Ice Age period, where the glaciers in the Swiss Alps, for example, expanded down to the valley floors, as you can see on the right side. And you see here that the temperature reconstruction from 1750 onwards, you see very large variability of past temperatures with a lot of negative extremes. And then, of course, in the last couple of decades, the warming is the overwhelming signature. And if you look at the total forcing and the volcanic forcing, then also becomes clear that the volcanic forcing forcing is the key engine of these large climate fluctuations in the late Little Ice. If you don't projections now and project forcing in the future, then of course we are taking into account estimates of CO2 emissions in the future, but we currently assume that no major volcanic eruptions will take place in the 21st century. And that is because we cannot predict the exact year where such volcanic eruptions would happen. But the IPCC is also trying to justify this by also putting observed volcanic forcing of the 20th century into a long-term perspective. And they argue that the average and variability of volcanic forcing is not unusual in the 20th century compared to the 2,500-year record with medium confidence. And I'm jumping now a little bit into the methods already. So this is now the latest reconstruction of stratospheric sulfur injection from volcanic eruptions over the last 2,500 years, merged with the satellite data for the last 40 years. And you can see that volcanism has changed widely between very active periods like in the 19th century, the 13th century, but also very quiet periods in the Roman and medieval time periods, for example. And if you now do the math and just calculate the teragrams of sulfur injected by volcanoes per year for the 20th century and compare that with the extreme centuries of extreme volcanism or extreme quiescence, then you can already see that it's quite a solid statement that the IPCC made, but I think that the confidence level is even higher than they currently admit. So I would say this is virtually certain that the 20th century was nothing anomalous in respect. So how can we do this? We can do this because a sample of the sulfate injections from volcanic eruptions is basically captured in the polar ice cores in Greenland, as you see here, but also in Antarctica. And if this is now the Greenland and Antarctic ice sheet, then you have snowfall throughout the year, and occasionally you have large volcanic eruptions, and these inject large amounts of ash, but also sulfate aerosols, and they get eventually deposited on this ice sheet, and then they get covered with a subsequent snowfall, they get protected and preserved, and you can find volcanic eruptions going hundreds of thousands of years back in. If you drill an ice core through these ice sheets, take them into the lab, then you can analyze the impurity content of the polar ice sheets. And you see it's here very slowly moving on the left side. So these are continuous melt procedures where you decontaminate the ice samples, but at the same time you're also analyzing it for a large suite of elements. Some are noted here. And I think the most relevant ones are those that are linked to characterizing this volcanic fallout. So this black layer in the graph on the left side. And this is, for example, acidity, sulfur concentrations, metals, or particle size distribution. So those are characterizing volcanic emissions of the past. These measurements also have some parameters that have very strong seasonal cycles, which allow us then to count the layers in the ice cores, very similar to tree rings, so we can determine the exact age of these volcanic eruptions. And that's how the principal method works. So we are looking into glaciochemical records drilled at the ice sheets, and we make estimates of the original SO2 injections by volcanic eruptions based on the observed sulfate concentrations in the ice sheet. Sometimes, if you're lucky, then the past plume might have passed across these ice sheets, and then you get additionally to the sulfate aerosols also deposition of ash, which is coarser and more heavier. So therefore the lifetime and the spatial spread of the tephra is typically not as uniform as for the sulfate. But this is having a very distinct geochemical composition, carrying the information from the magma composition, and then would allow you to trace back the individual volcano that is responsible for the sulfate deposition. And there are also emerging techniques like sulfur isotope analysis, where you look into the isotopic composition of the sulfate, which also constrains the relative height of these emissions relative to the ozone layer, which is also important to figure out the relative proportion of stratospheric input to tropospheric input for a given sulfate deposition event in the ice sheets from Greenland and Antarctica. If you now combine basically all these different methods, then you can answer these four important questions. When did the eruption occur? Where did it happen? How much SO2 was injected into the stratosphere? And how high was the atmospheric emission? And I think this is what Lauren Marshall will later explore in more detail. So she called this the eruption source parameter, which is a term that is characterizing parameters that are important for the radiative forcing that these volcanic eruptions impose on climate. But since this term is already used for a different context by volcanologists, one could also consider calling it emission source parameters, because it's really centered on the emissions of sulfuric gases. So you can imagine the day-to-day work that we are doing as a kind of criminal investigations like CSI cases where we try to solve cold cases, so trying to solve mysterious eruptions that happened in the past and trying to find out how these impacted and how they affected global climate. So the ideal traces to link such eruptions are instantaneous events with widespread distribution of fallout in a unique composition. And I'm just showing you now one example. So this is now sulfate. That's from Anja Schmidt's simulations of the Laki eruption 1783 in Iceland. This was injecting large amounts of SO2, which conforms and converts to sulfate aerosols. And these sulfate aerosols are then covering large parts of the northern hemisphere after this long, several month long lasting eruption. A different trace that we can find is then the ash and the tephra. And this is now a simulation using forward modeling of ash. See, it starts now. So this is Antarctica, and you have an eruption, Taupo, in New Zealand erupting, and that is distributing ash particles across the southern hemisphere westerlies, which then get deposited on the ice sheet in Antarctica. And a third trace is then not linked to the ice core record, but more to other proxy records, and that is the climate anomaly itself, because a widespread, extreme, and long-lasting cooling is rather unique signature for volcanic eruptions. So if you find large climate anomalies across large spatial scales, then these are typically caused by volcanic eruptions. And you can trace them, for example, in proxy records like tree rings, which have, of course, a higher precision and accuracies than the ice core chronology. If you talk about the terminology of criminal cases, then the thing that we try to do is basically we try to link the victim to the weapon, which is a sulfate, and then through the fingerprint also identify the culprit, so who's responsible for these anomalies, and in terms of sulfate emissions, but also in terms of climate. So that's what we are trying to do. And this is how, for example, artificial intelligence is imagining our work. In reality, we are working a little bit on cleaner conditions. So this is now a little bit the workflow. So we drill these ice cores, make long measurements covering many thousands of years, and then we go back again into the freezer, collect archived ice cores to resample specific periods where we expect to find tephra, so we can also link then the anomalies that we see in the ice cores to specific volcanic eruption. And I will better show this now on a specific example. So this is now case study 1 between Julius Caesar and Justinian, so looking into Roman time periods. And starting here, so this was in 2019. I went to the Desert Research Institute, where most of these measurements have been done. And they have just recently, Joe McConnell and his team at the Desert Research Institute were measuring the North Grip ice core from Greenland, which is seen here. This green line, that's the sulfate concentrations in the year, basically, after Julius Caesar has been murdered, 44 BC. Time is going from left to right. And you see this is lasting for about 2 to 3 years, the sulfate anomaly. But just at the rise of the sulfur concentrations, you see a very sharp layer of coarse particles. So this is ash particles, 3 to 10 micrometer in size and even bigger. And that's the diagnostic criteria basically for the presence of ash in these ice cores. And since I was already in the US, we put in a sample request to assess the very same event in an archived ice core in Denver. So Denver is the big repository where all the former ice cores have been collected over the last 50 years. And we were basically interested in looking at a very specific section that would contain the ash of this volcanic eruption, so we can do fingerprinting of these specific. And this is a little bit comparable to Harry Potter looking in the Ministry of Magic for a specific prophecy about Voldemort. And that's how I also tried to basically find a very specific piece of ice. You see it here in 480 meter depth. This piece of ice should contain tephra of this eruption based on these existing measurements. And we were actually, we could find tephra, and we could geochemically characterize it. So you can measure the elemental composition ratios of certain major oxides. And those have a very unique composition that then can be linked to a specific source. And that's what you see here in the red dots. So those are now the ice core measurements, and how they compare also to other known eruptions at that time, like Etna, Furnas, and other eruptions. And you have a very strong correlation with this greenish and purple dots. And those are samples that we also measured in our lab, but those are not from these other eruptions, but these are basically from our suggested candidate, and that's this caldera of Okmok in the Aleutian Chain, so a very large caldera-forming eruption, which then was radiocarbon dated to around 2,000 years before present. And we collected basically tephra in the forefield of this volcanic eruption in order to pinpoint our ice core tephra to this specific volcanic eruption geochemically. And this is a comparison now. If you see on the same scale a comparison to the well-known Tambora eruption, then you can really put this size of the caldera into the perspective, and we can then basically figure out all these emission source parameters that are really critically important to constrain the radiative forcing. So we estimate that 100 megatons of SO2 have been injected at elevations larger than 30 kilometers at 553 degrees north in fall to winter 44-43 BC. In this input parameter, we can then put in a climate model, and then we can make simulations how we suspect that this volcanic eruption might have impacted climate on regional to global scales, on different seasons. And we can evaluate these model output by looking into proxies, so certain proxies available, tree ring records mostly from the Alps, from Ireland, Scandinavia, and the United States, but also speleothem records. And then we can also put this reconstructed and simulated responses into a context of what people have been observing at the time based on historical accounts. For example, Brutus was describing very bad and harsh and snowy weather during his, so there was a civil war was going on, and they were with large armies in the field, where at the same time Cleopatra was not able to provide grain to the Roman Empire because they were suffering subsequent Nile failures for 2 consecutive. And using now, of course, the model output, we can put these into a perspective. So we see very strong cooling, especially in the northern hemisphere, very strong magnitudes lasting for 2 years after this eruption. And this strong cooling is also then pushing the ITCZ southwards, which displaces all the rainfall regimes, which leads to a very wet climate in the Mediterranean, but also very dry conditions in the headwaters of the Nile River, which would then also explain why the Nile River might have flooded due to the external forcing caused by this volcanic eruption of Okmok. So we're not saying that this volcanic eruption was monocausally causing either the end of the Roman Empire, the end of the Egyptian Ptolemaic reign, or it's somehow linked to the death of Caesar, but we are just providing a very important piece of additional evidence for contextualizing what happened around this time. If we move 600 years towards the present, there's a very similar event, so even bigger, because you have a very large eruption in 536 being followed by an eruption in 540, also as big as Tambora. And of course, the combined clustering of this double eruption had even stronger impacts on the surface climate, as you can see here on the left side on the tree ring width anomaly. But also on the right side, you see it that, for example, there was strong frost in Mongolia, but also in the western United States from this large volcanic eruption. And this was also a very critical, important moment, because just 5 years after the first of these 2 eruptions, the 536 event, which is also the one that people have been linked to the Fimbulwinter saga and experience of people from Central and Northern Europe. So just around 5 years after that, the Justinian plague was introduced to the Roman Empire in 541. And there's a continued debate about the role of external forcing, but also climate variability and diseases in basically contributing to the final fate of the Roman Empire. The second case study is going now to the quest for Terra. Terra is another very important volcanic eruption, Santorini in Greece. So it produced a very big ash cloud that is covering large areas of the eastern Mediterranean under ash, and is a very important time horizon that is linking the history of Egypt, the Levante, and Greece on a timeline. But the problem is the absolute age of the eruption is very poorly constrained. So there's a long quest for finding Terra and dating Terra in the science discipline working on that: archaeology, paleoclimatology, volcanology. In the 1980s, there were actually 3 Nature papers all claiming they have identified the exact year when Terra took place. And one of these is linked again to this frost rings, a very strong frost rings occurrences in 1627 BC have been argued to present the cooling following the Santorini eruption. At the same time, the ice core researchers found a very strong sulfate anomaly, which date 1628 BC if you shift the chronology to the now accepted New Age model. And you can also see that the spacing between two subsequent sulfate anomalies and two subsequent frost ring anomalies is matching up pretty well between these trees in the ice core record. But the question is still, is this Terra or is it not? And that's why we also sampled this event specifically in very high resolution. And just as I said with the Okmok case, we also found again cryptotephra shards at the rise of the sulfate peak, which allows us now to geochemically characterize this. Again, showing here this purple dots relative to these grayish ones. So these are correlating very well. And that's the volcano that I'm just introducing, but they are not at all matching the geochemical composition of the Terra eruption indicated here in white. And so we can close the circle, so we can attribute the tephra and therefore also the sulfate anomaly and the frost ring occurrence to an eruption of Aniakchak, which is again another eruption in Alaska, very large caldera, very big volcanic eruption. And that's certainly a big achievement, but I think that the quest for Terra is therefore not solved. So I think that it's still ongoing. So the debate for Terra has not been solved, but we've found at least another important climate impacting event that contributed to cold climate in this time period. Now I'm making it a little bit broader, the full Holocene, so we can extend these chronologies now, not for the last 2,500 years, but really to cover the full Holocene using ice core records like Waste Divide and others from Antarctica. And then we can come up again with a distribution of sulfur injection for the last 11,000 years, which you can see here. Of course, much less is known about the large eruptions throughout the Holocene, but that's also something that we hope we can improve going forward. And then if you introduce these forcing over the Holocene into a climate model, then you can also see that actually the Holocene has seen much stronger climate variations in the past that can currently be resolved in large-scale multi-proxy compilation because of the limiting dating accuracy and resolution of many proxy records. So that's what you see here. There's recurrent cold periods like the late Antique Little Ice Age, like the Little Ice Age, or also similar events throughout the Holocene. And I think I'm skipping the Lachersi and Younger Dryas study because I want to focus a little bit now on the impacts of volcanoes on human society, because that is also a long theme. How much does climate or volcanism or both, a combination of both, impact human societies? And there was a recent review paper by Ulf Bündgen, Clive Oppenheimer and colleagues, where they were basically collecting papers that have been done in the last 50 years or even more on such associations. And also Climate of the Past has been one of the key papers promoting this research. And you can see, of course, it was getting a lot of attention starting around 2016. And I think this is due to the resolving prior inconsistency in the ice core dating, which of course produced inconsistency in the volcanic forcing, which were resolved in 2015. But then we also founded this PAGES working group, Volcanic Impacts on Climate and Society, where we are looking as interdisciplinary teams with archaeologists, historians, modelers, and paleo proxy people, the effects of volcanic eruptions on climate. And there was a special issue also in Climate of the Past on this. And I think there's even more room. So this is now just focusing on work that has been done for the last 2,000 years. I think there's a lot of potential to extend this further back in time. I think I could convince you that we are approaching an area where we have very close to annual resolution time series of climate, but also of human responses going back 4,000 years. So we can basically looking into this new data and try to re-evaluate current existing studies that have been looking into potential impacts of climate or volcanoes on human societies. And there's quite a bunch of studies that have been performed. And I think we can populate with this with ever more fine-grained detail in terms of spatial resolution and also dating accuracy. And another view is going forward. So we also, I think, can use the past a lot to make informed projections about the future. This has been partly done by Ingo Bethke and all, but focusing on global air temperature projections. And of course, we can see that the long-term trend of climate is given up by the emission scenarios. But I think the way, so this uphill trend is clear, but the way might be much more bumpier than we expect if you have a much very strong volcanic future we might experience periods with a small warming hiatus, while at the same time, after the effect of the volcanoes are dwindling, then you have, of course, a termination shock. So basically increased warming rates after volcanic eruption. So there might be a much bumpier road ahead of us going into the 21st century if you consider extreme scenarios of volcanic eruptions as they have occurred in the past. And I think with this, I'm done, and I'm happy to answer any questions later on. And I also would like to acknowledge all the co-workers, PhD students, and collaborators on this project and the financial fund. Thanks.
Thanks a lot, Michael. So I remind you that you could already pop up your question in the Q&A box, and the two speakers will answer after the second talk. And this second talk will be given by Lauren Marshall. Lauren is currently a research fellow at the School of Earth and Environmental Science at University of St Andrews. She has completed her PhD at the University of Leeds. She had also worked in Cambridge and in Durham. So her work focused on understanding the impact of large volcanic eruption in climate, but this time a bit more on the modeling side, and in particular to try to understand how the different properties of different eruptions affect the impact, and for example, the amount of sulfur dioxide that is emitted or the latitude of the eruptions. So she has worked a lot with the UK Earth system model to simulate the eruptions, in particular over the last millennium, and we are looking forward to have more details and information about her recent work. You have the floor, Lauren.
Hope you can see that okay. Thank you very much for the kind introduction. So I'm going to talk today a bit more on the climate modelling side, and in particular how we represent these volcanic eruptions in climate models. And so with thanks to many co-authors, and also to those or anyone kind of involved in the running of PMIP4 simulations. These are quite hard to set up, and a lot of work goes into these model simulations. So Michael has kindly set the scene really nicely for me, so I won't go into a lot of detail on some of the background, but just as a summary, these volcanic eruptions, ones in which the SO2 is emitted high into the stratosphere, can lead to a wide range of impacts on the atmosphere and the climate. So volcanic eruptions, they inject a cocktail of gases into the atmosphere. But for the climate impact, we are mostly interested in that sulfur dioxide emission, and that's because that sulfur dioxide is oxidized into sulfuric acid vapor, and this then condenses, nucleates to form sulfur aerosol, which is a very good scatterer of incoming radiation, and this leads to surface and tropospheric cooling. However, that aerosol itself is also a very good absorber of infrared and long-wave radiation. This leads to a localized stratospheric heating, but it is the surface and the tropospheric cooling that we tend to focus more on. This is the dominant effect. But together, these two aspects then lead to follow-on impacts, such as changes to clouds, to precipitation, shifts to the intertropical convergence zone, that Michael's already mentioned, maybe impacts on vegetation and on the ocean. So there's a lot of things to go into and to understand. Before I go into some of the modelling results, I just wanted to highlight again the two kind of key metrics that we look at in the models and also in observations when we have them, which is the aerosol optical depth, so the amount of or how much the solar beam is being extinguished by the presence of aerosol. And this is an example following the 1991 eruption of Mount Pinatubo. You can see the eruption occurs, and then we have a peak in the AOD around about 6 months after the eruption as the aerosol has formed, and then a decay which lasts about 3 to 4 years. And then we have the radiative forcing, so that's that energy imbalance, and we tend to look at this at the top of the atmosphere. After that eruption, again, an example here following 1991 Mount Pinatubo, we have a strong shortwave volcanic forcing, and that's because that aerosol is reflecting radiation, more energy is going out, and that's that cooling effect. We have this smaller warming impact here, that's the long wave volcanic forcing because of the absorption of some of that radiation in the stratosphere. But the net of the two, shown in black here, is a negative forcing, which is cooling. And so I'll come back to some of these plots a little later in this webinar. So of course, if we then look at, this is a simple climate model simulation from 1950 to 2000, we can then see that we get sort of short-term interruptions in the long-term warming trend due to these large magnitude stratospheric SO2 injecting eruptions, and the last of which to have occurred was that in 1991. And so eruptions are the most important natural driver of climate variability, and therefore understanding their impact on climate is vital, not only just understanding their effects, but also to compare with other drivers of climate variability, such as anthropogenic. So bringing back then to the last millennium, volcanic eruptions have also been a major driver of climate variability over the last millennium. Here's a figure here from the latest IPCC report. There's variability, but there's also clear kind of cooling episodes because of volcanic eruptions. However, there is a kind of long-standing problem in this field, whereby the volcanic cooling that is simulated by climate models following these eruptions tends to be larger and also shorter lived than that from tree ring reconstructions. And that's shown here in this figure on the right. This is a superposed epoch analysis, so it is an average temperature response following several large eruptions that have occurred in the last millennium. And in the grey are the results from CMIP5 models. So they indicate that on average, following several of these eruptions over the last millennium, the cooling is around about 0.8 of a degree, and black is the ensemble mean. And then there are 3 tree ring reconstructions shown by the colours here. And so the peak is stronger in the models, but it also decays, the forcing also decays a lot more quickly than in the tree ring records. And so the study that we conducted was to kind of look into this discrepancy in a bit more detail. Why is that? Is there anything that we can do to resolve this? But before I get into those results, something that we need to consider first is, well, how do we actually simulate volcanic eruptions in climate models? And there are several ways. Most climate models require an input of the aerosol optical properties. So that's things like the extinction, so how much kind of a proxy for how much aerosol is there. Also things like the size of the aerosol. And that's what most climate models require for the Earth system models that run these simulations. Some models can run directly with the volcanic SO2 emissions, and these are known as interactive aerosol models or aerosol climate models. And then some models actually require the radiative forcing itself as input, and several of these models are used as part of the IPCC reports. And of course, Michael's talked a lot about sort of how we get to some of these emissions. For the satellite era, we have observations, but for the past eruptions, it must be reconstructed. And again, very briefly, that aerosol ends up on the ice sheets, must be kind of composited in a way to get a kind of average deposition. That's then converted to the sulfate burden, which gives us an estimate of then what the SO2 emission was. And that's based on a scaling factor, also called a transfer function, which is often based on what was observed and modelled after the 1991 eruption of Mount Pinatubo. And so assuming that we're happy with this, I mean, there's a lot of uncertainty and a lot of work being done in regards to this conversion factor, we can then get a time series of volcanic SO2 emissions for eruptions over the last millennium. But some of those models, they require the optical properties. They can't be run with the SO2 emissions directly. That's because those models are often more complex. They need a complicated aerosol scheme. Those simulations tend to be more expensive, both computationally and also in regards to time. And so we could use a subset of those models, the aerosol climate models, to get the optical properties from the SO2. And an example is shown here from a study of Mount Tambora in 1815. This is the global stratospheric aerosol optical depth across several aerosol climate models. So they've taken the SO2 emission of 60 teragrams, run it through the model, and this is what they get for AOD. And what we find is that there's a large spread. So even though the SO2 emission is the same, the optical properties and therefore the resultant impact on climate is very different across these models. So for the models that need the optical properties, what should we take? What was kind of decided and a tool that was developed was the Easy Volcanic Aerosol Forcing Generator, which is a more simple transport model, but physically based and calibrated against known eruptions, that again takes the SO2 and spits out the optical properties that can be used for other models. And so here showing the zonal mean aerosol optical depth following Tambora. Again, it's lasts on the order of a few years, and the global mean here for Pinatubo. And then for the last millennium, or indeed even longer, we can get a time series of optical properties from EVA, the Easy Volcanic Aerosol Generator. And the result of this for Tambora is actually shown by the red line in this plot here. And so it fits nicely between the kind of spread of these other models. So it's a good approximation and a good kind of volcanic forcing to use going forwards. So to summarize, 2 ways of simulating these eruptions. We used optical properties, and this was what was kind of used mostly in the PMIP4 protocol and in previous generations of models, this data set here. Or if your model allows you to do so and you have resource available, you could use SO2 emissions. The main difference here is that the sulfur aerosol that is formed in these models is formed online, and so it can then interact with the chemistry scheme, the dynamic scheme. If there's a change in heating because of the presence of aerosol, which leads to a change in the atmospheric dynamics and winds, then that aerosol will move and be transported appropriately with those changes. We're still not accounting for emission uncertainty. That's still something yet to be included, but we can simulate the eruptions a bit more realistically in this way. So coming back then to that question of, well, can we reconcile model and tree ring cooling? There's kind of 2 reasons that this could be. Either it's a limitation in the tree rings, things like biological memory effect or uncertainties given the kind of spatial representation, or back to the model limitations. Up to this point, most models have prescribed the optical properties, and something we wanted to look at in this study was, well, what difference does it make if we run the last millennium using SO2 emissions for volcanic eruptions? And this is what we did. We ran the UK Earth system model. The simulations themselves took over 1 physical year to run, so it's not something that I think I would like to do again, but we've got a great data set there now. We then compared with other models that were available at the time that had also run the last millennium. So we ended up with 6 models in total, and of these, 3 used the SO2 injections from this eVolve2K dataset, which is the SO2 emissions derived from ice cores, and then the remaining 3 used the aerosol optical properties derived from the Easy Volcanic Aerosol Forcing Generator. And this is what that volcanic SO2 dataset looks like, again, similar to some of the plots that Michael showed earlier. And one thing to kind of draw out from this, again, is that given a lot of the uncertainties and potentially the lack of tephra or other fingerprints that we have at the moment in this dataset, a lot of the eruptions continue to be unattributed to known volcanoes. And so if there are simultaneous signals in both Antarctica and Greenland, we assume this eruption was tropical and it's given a latitude of 0 degrees. Likewise, if only one signal is seen in Greenland, then it's assumed this is an extratropical eruption given a latitude of 45 and similarly minus 45 for eruptions with signals only in Antarctica. So the first thing that we can look at then is that stratospheric aerosol optical depth in these simulations. And this plot is showing in 100-year chunks the AOD across this simulation. So starting here in 1250 down to 1650. And for the models that ran with SO2 emissions, so that's UK ESM, CSM2 in grey, MRI ESM2 in this kind of olivey colour. There's quite a lot to pick out here. There are differences for individual eruptions, but there are some key take-homes that are a bit more consistent across some of the large tropical eruptions. And one of the main things we find is that the peak AOD tends to be stronger in these other models compared to the EVA dataset. So that's the dashed black, which is the dataset used when models need to prescribe the optical properties, and differences in the decay time. So CSM seems to last longer, UK ESM, the decay is a lot quicker. That's also the case for Tambora in 1815, that's shown here on the right. But then if we look at Laki down here, again, differences, EVA having a longer lived forcing than some of the other climate models. Now, of course, any difference in aerosol optical depth is going to travel through to the surface air temperature. And this figure is showing that global annual mean surface temperature now for all models that we looked at. So the 3 that had SO2 emissions and then the 3 that prescribed the aerosol optical properties. Few features to unpick straight of all. I mean, we've got variability there. We've got a clear impact of the volcanic eruptions over this period. CSM2 seems to warm over this period. And then if we look at the big eruption of Samalas here in 1257, then a much stronger temperature response in CSM2. The other models seem to have a more similar cooling impact. The next step then is to look at the summer northern hemisphere surface air temperature. Now this is what is kind of closest to what we think those tree ring records represent. And again, a lot of variability, big responses, again in CSM2 following the big eruptions, a lot of different things going on, some deviations, some similarities. If we then look at the tree ring reconstructions, so 4 tree ring reconstructions here, variability is not as large. There are differences between the tree ring records, but again, still impact following some of these large eruptions. So a lot to look at on these time series. One way that we can try and compare the models and the tree ring records is to go back to this superposed epoch analysis. So really just looking at what the average cooling is over several different volcanic events. And that's shown here on the left in this figure. This is showing the average cooling in that tree ring target area, so Northern Hemisphere summer, in the 6 different models in the coloured lines, and then the 4 different tree ring reconstructions in the black. And what we find is that actually there are some models, IPSL, you can kind of see in this pink line here, that compares quite well with one of the tree ring reconstructions. So there is a kind of more muted response in this model. There is still a generally larger cooling in the other models, and especially in CSM. But there isn't a clear kind of distinction between the models that prescribe the optical properties and those which used SO2 emissions. This average response here is looking at 10 different eruptions, and of course these eruptions also have different emissions, different seasons, slightly different locations, so there's a lot kind of going into this, but as a whole, on the average and kind of comparing to that previous generation, there's still an overestimation compared to the reconstructions, but perhaps we're getting closer for some of these events. If we then look at just the largest 3 eruptions, so these are the 1257 eruption of Samalas to begin with, we can see slightly different things going on. We actually find that UK ESM and IPSL compare quite well to the tree ring reconstructions in the sense that there is a more muted cooling, but still a larger cooling for some of the other models. And this is similar for 1458 and 1815. However, these eruptions are a bit more complicated because of eruptions that occurred just before. So these are those kind of double events that Michael alluded to earlier. 1458 is also an interesting case because there isn't a large signal in tree ring records, but again, a lot of variability among the different models. So because of that, and because there wasn't a clear kind of distinction between models that had used SO2 emissions and models that had prescribed optical properties, there are also model differences that are leading to some of these different responses. So even though you might use the same optical properties, the way that that's translated into radiative forcing is going to differ. The climate sensitivity of the model is going to mean that that response could also be different. And so we decided to take the same model, UK ESM, and run 2 sets of ensembles of simulations, one with SO2 emissions and one with prescribing the optical properties, so that we could really see the difference of the method in the same model. We focused on just the 3 largest eruptions, so Samalas 1257, then the unknown eruption in 1458, and then Tambora 1815. And what's shown here in this figure, firstly, is the zonal mean aerosol optical depth in the EVA dataset. So that's, again, which goes into the models that don't have aerosol chemistry climate schemes. And then in the pattern, in the plots in the middle here, what UK ESM simulates for aerosol optical depth. And in the bottom here is the global and northern hemisphere mean. So the first thing to kind of pull out from this is that in the EVA data set, first of all, the AOD lasts longer, but it's more hemispherically spread. It's more kind of globally even. And in UK ESM, we tend to get this much stronger localized AOD and a higher peak. And so the global mean and the northern hemisphere mean tend to be similar in the EVA data set, but we get this much stronger asymmetry in UK ESM. And that's also the case for the other 2 eruptions. So more hemispherically even, stronger peaks in UK ASM, and a stronger asymmetry, especially for 1815 and 1257, much stronger AOD in the southern hemisphere. And so the take home from this is that the spatial pattern of forcing is really different. Now, if the spatial pattern of that AOD is different, that's also going to then follow through to the radiative flux anomalies, and that's shown here in this figure. Again, zonal means. We have higher peak values for the emissions-driven case studies, so that middle panel here, a kind of more even spread in the prescribed data set, which leads to differences in both the timing of the peak and, of course, where that peak occurs spatially. And if we follow that through to temperature, again, zonal mean surface air temperature anomalies mirrors exactly what we see, not exactly, but sort of the overall pattern of what we see in the radiative forcing. And what's most important then is if we look in the region where we're looking at our tree ring records, so the northern hemisphere, sort of 45 to 70, because of the difference in spatial spread, we actually have much stronger forcing in this region in the prescribed setup, and so stronger temperature anomalies, whereas the forcing in these emissions-driven cases tends to happen for 1257 and 1815 in the southern hemisphere. Opposite case for 1458, we actually had a stronger transport of aerosol to the northern hemisphere, and we end up with a stronger peak temperature response there. And so finally, if we then follow that through and look at the northern hemisphere summer land temperature only and compare those two ensembles, we can then see the difference in temperature because of that method. And so for 1257, shown here is that temperature anomaly, northern hemisphere summer temperature anomaly in black in the prescribed simulations and in blue in the emissions-driven simulations. The bold is the ensemble mean, but then we have ensemble members here too, and there's quite a variability. So that's something that also came out, are these differences and these discrepancies just because of internal variability? But we can see that in the emissions-driven scenario, the peak is sooner, it's in the first year after the eruption, and it's not as large, -1 compared to just over -1.5 in the prescribed setup. And this peak also occurs in the second year. And this is also important then for tree rings, especially given thinking about the timing of when the aerosol forms versus when that growing season is. It's really important that we know when the kind of peak forcing is, because that then follows through to some of these reconstructions. If I draw your attention to the last panel, to 1815, again, we have the kind of similar story to 1257 Samalas, stronger cooling in the prescribed versus the emissions driven. 1458, we have a much stronger cooling in the emissions driven scenario because this eruption occurred in January in the winter. The Brewer-Dobson circulation, which moves aerosol from the tropics to the northern hemisphere, is stronger in the winter. We get a much stronger transport to the northern hemisphere and therefore a sharper cooling. We did test the sensitivity to season because this is an unknown eruption, and we find that if the emission was in July, then those simulations actually compare more with that kind of prescribed setup because we end up with more kind of uniform aerosol distribution. So we are finding that we have a smaller peak northern hemisphere summer cooling for Samalas and Dombora if we use SO2 emissions. It's not the case for 1458, but there's a lot going on in terms of unknown season and other kind of eruption parameters and the effect of double events. So to conclude, we're finding that the models are still overestimating cooling compared with tree rings if we look at kind of the average response over lots of eruptions during this period. We found that aerosol modelling might perhaps reconcile some discrepancy between the tree rings and climate simulations, in particular for Samalas and for Tambora, so two of the largest eruptions. And really this is coming from the spatial structure of the volcanic forcing. So we're still saying that it's a tropical eruption, we're still saying that you can get bipolar signals, but perhaps there could be an asymmetry there, which means that there is less aerosol or a lower forcing in the northern hemisphere, which then means a lower temperature response. There's clearly still a lot of other uncertainties. These simulations are expensive and time consuming. And so one of the kind of remaining questions is how do we then better sample some of these unknown eruption parameters? And of course, with Michael's work, once we sort of know some of these eruptions, or we can attribute some of these eruptions, then we can add more of these properties into the climate model simulations and reduce some of these uncertainties. But this is a big question going forward. And that I will leave you with. Thank you very much for your attention.
Wonderful. Thank you. Thank you so much, Lauren and Mark, for those excellent presentations. I think they provide a really nice overview that is you don't require a PhD in either volcanoes or in modelling done in either of those. So thank you very much. I'd like to encourage everybody who's here, if you have any questions for our panelists, please pop them in a box down the bottom. Hugo and I will be monitoring those. We've already had a question from Alejandro, which Michael has kindly answered, which you can read there. And while the other questions are coming in, Lauren, I have a question for you, if that's okay. I'll just speak it. And if you have a question that you'd rather voice verbally, please raise your hand. I'm curious about the role of recent volcanic eruptions. I'm thinking about the Hongatoa eruption in Tonga a few years ago. How much do recent eruptions inform the next round of modelling in terms of, we saw a lot of water vapor and other things spread around from that volcano, and we were able to see in real time how these things kind of spread. How long does it take for a volcanic eruption to happen in the very recent past to make its way into the models, and how does it?
Yeah, absolutely. I mean, I think every new case then provides a test bed for the models, right? And there's a big kind of a model into comparison project looking at specifically at Hongatonga, and so then we can use that as a test. Do we get the right aerosol distribution? Do we get the right forcing? And of course, that then leads to model development in the sense of kind of tweaking some of those parameters maybe to try and to match. And then of course that then feeds back into your past simulations as well. So it is kind of every model comparison study. We've then got more information that we can then kind of add in, and then we come to kind of these big, whether we're now moving to PMIT 5, we sort of repeat some of these experiments, and we've got better data sets that go in there. So yeah, it feeds in eventually. Again, with different emissions, right? We sort of focused on SO2 right away. Now there's a renewed importance of adding in that water vapor too. And that, of course, is going to change the rates to forcing. So we're just, in these simulations that we did, we're just putting SO2. We're not considering halogens. We're not considering water vapor. And so, of course, that could then, counterbalance or add to or something to the rates of forcing. So in that regard, it's more uncertainty. So how much do we want to change things? But yeah, I hope that answers your question.
Interesting. Thank you. Please pop your questions in the chat. I've got a list of questions. I'm happy to keep asking mine, but it would be much more enjoyable to hear from you. Michael, I've got a question for you about, I really enjoyed your presentation and seeing the connection between historical events, not saying it's climate determinism, but thinking about the impact that these volcanic eruptions had on society in the past. If we think about, there seems to be a renewed focus on future potentially high impact, low likelihood event. If you were a betting man, do you have an idea of a particular volcano, a particular region in the future that you would be keeping an eye on for a volcanic eruption that is unlikely to occur, but if it did, it would have huge societal ramification? Or you're muted.
I think it's very difficult to put a finger on a specific volcanic eruption because all the last eruptions in the past, like Pinatubo, Tambora, Hungatonga, they have never been very active in the centuries leading up to that. So every major eruption in the last 30, 100 years that happened came basically as a surprise. So I think it's difficult to just judge from an individual volcano if that is one that could pop up again in the 21st century. But I think looking at the overall record, so if you have this 10,000 year record of sulfur injection, that gives us a little bit of a possibility to estimate the frequency of very large volcanic eruptions. So we can say that there's a chance of 1 to 6 that we experience a Tambora-sized eruption somewhere on the globe within the 21st century, but we cannot tell which one it is. That's, I think the problem that we cannot put the finger on the event, but we can constrain the probability of very large eruptions, which we cannot do using the satellite era because they are not covering the large eruptions.
And do you feel as though future projections and future considerations of possible scenarios incorporate volcanic eruptions enough?
Yeah, I think they should, because we must assume, looking into the past, that they will happen. And of course, you cannot do it with the most expensive, highly coupled model runs, but you can explore simple energy balance models to see what the effects would be if a Tambora happens every 20 years or a Pinatubo every 40 years, something like that. So I think it's possible to play around with the impacts on future climate, our past knowledge.
Thank you. Many thanks for that, Michael. Lauren, I've got one more question for you, if that's okay. Hugh, if you have a question as well, feel free to interrupt. But I was wondering if you could tell us, Lauren, a little bit more about what you think it is about UK ESM that's giving it that slightly different result to what you expected.
Yeah, we think latitude is quite important. So for those two eruptions, they're at -8 degrees south. And so normally, if it's an unknown eruption, they're put at 0 degrees. And we still think of these kind of tropical eruptions, or maybe a band between 15 south and 15 north, as maybe having a similar behavior. But I think what our model showed in that regard is that just being slightly below the equator, and given the season that eruption happened in, because the circulation that's happening at that time is stronger to the southern hemisphere, those kind of conditions lined up, which meant that most of that aerosol, well, not most of it, but a larger proportion went into the southern hemisphere than the northern hemisphere, which is a bit different, I think, from kind of earlier thinking where it's like, oh, it's a tropical eruption, it's spread evenly, we kind of get this global kind of uniform spread. It is just one model, it's just one potential realizations. That, you know, there are many caveats with that model too. Maybe the kind of tropical pipe, the area where that aerosol stays in the beginning, maybe that's kind of held there a bit too long before it's then kind of dispersed. We're not sure, you know, of course, we're injecting a lot of SO2 into one grid box that's maybe 100 kilometers wide. So there's things to consider there. It could be plausible. So it's definitely something to think about. It's seen in another model, also this kind of southern hemisphere transport, a bit more for these eruptions. So definitely an area to explore a bit more, I think.
Thank you. Oh, it's a shame that they're such expensive models to run, isn't it? Because you could move the volcano up and down and around and change the month, and that would be fabulous.
Yeah, we've done a bit of work on that and kind of sampling some of that uncertainty, but there's a lot to look at, right? It's not just location, it's also height of emission. So in those simulations, that was a very fixed height. I think it was 18 to 20 kilometers. Of course, if you inject higher or lower, that's going to influence the lifetime of that aerosol and also where it spreads. So maybe that -8 degrees south and the fact that it all goes, or most of it goes to the southern hemisphere, is also caught up in the height that we chose. So again, a lot of uncertainty.
If I can jump on that, I was wondering, among all those uncertainties, if the specific atmospheric circulation during the year of the eruption matters. For example, if you are in El Nino year or not El Nino year, which is not necessarily well reproduced by your simulation, does it matter on the estimate of the response, and you see different between different members? Or maybe it could even impact, and that's maybe a question also for Michael, maybe it could also impact the amount of sulfates that you find in the air, in the ice cores, depending on the specific condition during that year. Is it something which is a dominant uncertainty, or is it negligible compared to the location, the amount, or the season of the eruption?
Yeah, where it ranks, I would say the SO2 emission still being the kind of largest factor there, but it does matter. Yeah, so that spread in the case study simulations that I talked about, we had 9 ensemble members, and they were chosen based on different ENSO and different phases of the QBO. And there is a very different spread in the amount of aerosol, whether it's an easterly QBO or a westerly QBO, which then has implications for the amount of aerosol that ends up over the ice sheets. So that's something that we do see on those ensemble members in the case studies. For the long UK ESM and also the other models for the last millennium, we were able to run 3 ensemble members. And again, so they will have slightly different QBOs, ENSOs. We haven't quite looked into the impact of that, but of course, more often than not, you can't run more than one ensemble for 1,000 years. So yes, it does matter. I think if you knew the SO2 and you knew the heights and everything, then also we would see a big imprint of this, but it's kind of caught up also in those other unknown parameters.
Okay, so if I don't see many other questions, so do not hesitate to write your question in the Q&A. But Michael, I was a bit, let's say, not surprised, but when in your plot, when you show the amount of the magnitude of forcing, the 13th and the 19th century were really anomalous years, but the period between the 30s and the 19th century was not clearly in your plot. So what is the current confidence in the contribution of the volcanic eruption for the longer term cooling between 13th and 19th century that you see in many regions? Would you say that yes, it's mainly the volcanic forcing that explains this little ice age or something like that, or is it still something which is debated, the contribution of the volcanic forcing to this event?
Thanks for the question. So this is really, I was just focusing on the three least active centuries and the most active centuries, but of course there's the 15th century is also among the larger active ones in the 17th century. So I think it's really a combination of having very many clusters of volcanic eruptions over several decades, plus 3 grand solar minima at the same time. And then of course the orbital forcing is also reducing the summer input in the northern hemisphere. So it's certainly, I think, a little bit of a combined effect of all forcings constantly going towards a stronger cooling, peaking then around 1800 to 1850, and initialized, I think, in the 13th century, but then it was somehow not constantly, because 1500 to 1600 is rather quiet, but throughout the last, let's say, 1450 to 1850, you always had very large eruptions plus solar minima. I think that's certainly a compounding effect of several negative forcings at the same time.
We've got a few questions coming in now through the Q&A, Hugh, so that's good. Question from Dr. Vishwanath about the reliability of the ice core sulfate record. How reliable, Michael, to you, how reliable would you say these ice core sulfate records are in reconstructing past volcanism, maybe in terms of where the uncertainties might be?
Yeah. So I think the sulfate measurements, they are highly reliable because there are not many sources of sulfate. So we subtract the marine sulfate contributions, so most of the peaks is then directly attributable to volcanic sulfate. And then the measurement of sulfate is not the critical thing. I think the largest sources of uncertainty then really relate to how you upscale from depositions across the ice sheet to global scale hemispheric burdens, because it's very difficult to calibrate that, because there's no good observations where you have basically observed sulfate depositions on the ice sheets and observed sulfate burdens, because in the Pinatubo era, for example, you have such high background pollution in Greenland that you cannot see these sulfate depositions. So I think that the calibration and independent validation of these transfer functions, that's, I think, the largest source of uncertainty. But I think if you just look at the repeatability, drilling several ice cores across Greenland, they all show the same. So I think there's a very strong coherence between the sulfate records for good sites. So not everywhere, but most of the sites are really coherent. So the source is not in the measurement, but really in linking it with good observations of stratospheric sulfate burden.
Another question from Malcolm Hart. As a micropaleontologist, I'm more concerned about the volcanic ash landing in the marine environment, which then takes down plankton and clogs the gills of pteropods. The eruptions of Montserrat don't figure on international scale, but the same happened at Mount Pinatubo. The climate impact of taking out the local plankton is probably not significant, maybe not insignificant, and would not figure in the models. Lauren, are you able to speak to whether that process is incorporated in the models at all?
Yeah, no, I'm afraid these types of models, we don't tend to include ash. I mean, that's something that we're starting to do now. So I think that's one of the model developments going forward, is to add ash. But again, these kind of big Earth system models, climate models, the resolution of the grid boxes is too coarse for that type of analysis. I think as things go forward and we kind of couple more of the regional like kind of land models and things, perhaps we'll be able to look at some of these effects. So not currently in these types of models, but I imagine that there's regional models that would look into this as well.
Interesting. Yeah, it's a really good feedback that I hadn't considered before. Many thanks, Mel. And a question from Christian, possibly to you, Michael. I had the impression in one of the plots that the decaying ice sheets impacted volcano activity. Are you able to speak to how certain that is, and how, and maybe then to you, Lauren? So Michael first and then Lauren, how it's considered in model simulation?
Yes, I think you mean the plot showing the Holocene volcanic activity. You see basically that in the early Holocene, until around 9000 BP, you have increased volcanic activity in Iceland. I think that's relatively well known and understood, that the rapidly retreating ice sheets were triggering a surge of volcanic eruptions from the mantle decompression. After you remove these big blocks of ice, you get more activity. I think that's good quantified in places like Alaska, Chile, Iceland. And of course, how is it considered in model simulation? That's, I think, a little bit more uncertain, because it's very difficult to then, those are difficult to assess because they're not looking like this typical sulfate spikes that I've showed you. So you're not having a short-term peak, but really increased levels of sulfate across many decades. And that makes it much more difficult to define the starting date rate and also the emissions. So these are maybe ground level tropospheric emissions. So it's not easy to put into a climate model, but I think that's certainly something that needs to be considered. How much do tropospheric emissions that can last for many decades and centuries contribute to the overall aerosol burden? But at the moment, people are focusing very strong on the stratospheric part, but I think there's also a story on tropospheric sulfur emissions from long-lasting eruptions.
Lauren, would you like to add to that?
Yeah, I mean, no, not much to add really. I think it also depends on the type of model that you're running, right? And again, to look way further in the past, we can't run these kind of aerosol climate models with that kind of resolution. But again, there's a lot of effort on kind of coupling the ice sheet modeling with this as well. So yeah, something to look at in the future.
Thank you. Many thanks both, and thank you to the questions that have come through. We've got a couple more minutes, so if anybody has any last minute burning questions, erupting questions to ask our excellent panelists, please pop them in chat. Do you have any final questions?
Yeah, I may have a question for Lauren about the modeling of those very big eruptions. So we do not have really a comparison with those very big eruptions like the one in 1257. So is there some specific processes associated with this massive injection of aerosols that we don't know well, that maybe aggregation of particles? And how is it modeled if we do not have observation for those big eruptions? And how is the uncertainties associated with those very big eruptions that may have different processes that are dominant compared to Pinatubo, for example, which was big but smaller?
Yeah, absolutely. I mean, so some of those, so the self-limiting effects, so the aerosol growth and the fact that they then fall out more quickly and they're less efficient at scattering radiation, that's included. And again, that's kind of all done interactively. So that's accounted for, and the model is then evaluated really only for Pinatubo, or that's the best that we've got in terms of maybe how big that aerosol was and where it went. Of course, big unknowns there are also some of maybe the dynamical aspects. If you've got a lot of aerosol and heating, and maybe some of those things change as well. So potentially there are different responses, but we don't know. Only that, those self-limiting effects are considered. That does mean that there's a kind of tail off in the magnitude of the forcing as we get to progressively larger and larger SO2.
But that's kind of models use treating those issues in the same way, or could it explain some of the difference between the different models? So
all of the models have slightly different aerosol schemes. So yes, of course, that does account for some of the differences. They'll all kind of consider those processes. They will account for the self-limiting effects, but they are most likely in different ways, right? Depending on how the aerosol schemes are set up. You can have modal schemes. We tend to have modal schemes, so the aerosol is distributed over different aerosol modes, and then the sizes. That kind of brings me actually to, we saw this much stronger response in CSM2, this much larger aerosol optical depth, which kind of follows through. And we think there's kind of two reasons for that. We think that probably is to do with the specific sizes that are used for the aerosol modes in that model, and then potentially then also like climate sensitivity to that change. So yes, yeah.
Okay, thank you. I don't know if you have other questions, Lyndon. I don't see question in the chat at the moment, but we are more or less at the end of the time that was allocated. So except if someone has a very last minute question that you can already start to write in the chat. But otherwise, I think I can thank you again, Michael and Lauren, for the very interesting presentation. And thanks to all of you for attending. I would like also to thank the people to contribute to the organization of those seminars at the EGU office, but also the Didier, who was really at the origin of those seminars and is managing all the process. So remember that next week, the next seminar, that will be the last of the series. It is scheduled for Wednesday, April 8th at 5 p.m. Central European time. It will be on paleoclimate of extreme events with two very interesting presentations from Jessica Pilar-Squix from Simon Fraser University and Jason Smurden from the Columbia University. So registration is available already on CP web pages. So there is one question on the seminars. They are available on the EGU channel, but you can also find a link on the CPE webpage if you want to get that. If I'm right, Denis, on the CPE website, you also have a link to the seminar, and you can find the previous seminar that are available. Okay, thank you very much, everyone, and thanks, and see you for the next seminar in 3 weeks.